I will note that this is part of why, like last semester, I realized that we had started with 12, and we ended up with 4. And that's because a lot of them decided, you know, I'm just not going to bother going to class. At the end of the day, you're all adults. You get to make your own decisions and live with the results. All right, let's see what we need to talk about today. First of all, assignment 2, lab 2, due, well, they're technically due tonight. Get them in if you can. I'm going to take everything. I'm going to try tomorrow. I'm dedicated tomorrow morning to just grading the first 2 weeks' materials. Yeah, you should have been able to get through them. But if not, talk to me. I want everybody to be, have them figured out. Next week we'll move on to lab 3, assignment 3. Like I said, we just keep building, so just stay on top of it. Let's talk about a couple other concepts today. We want to talk about resistance. So resistance is the opposition to the current I'm going to say conductor. I mean, we could have resistance for insulator. Usually we're not letting current flow. So resistance, the opposition to the current in some conductor. Units for resistance. Actually, we'll start. The other ones have done symbol first. So I'll do symbol. Symbol for resistance is easy, I should say. R for resistance. Units for resistance. Anybody know? Ohms. Ohms. You got it. So. Omega, Greek O, because, well, if you put an O on the end, it would look like another 0. So we just go with the Greek symbol. If you need to type it in anything, it shows up in the special symbols inside Microsoft Word and such. So, all right, ohms is how much resistance an object has to the flow of current through that object. And we'll be talking more about that direct relationship between current and voltage as we go further in the semester. When you look at Ohm's law, that's that relationship. All right, so now we know voltage, current, power, and resistance. Those 4 quantities are the primary thing we need for the first part of the semester. And we'll be working with those combined to build circuits out of them. So you really want to get those basics down at this point so you have them ready to go conceptually. All right. Now, the resistance of a conductor. I'm going to give you an equation, I'm going to explain it. So let's start with the equation. Equations are just pictures. So people say, picture's worth 1,000 words. Equation is just a really short, easy way to write something. So you don't have to write paragraphs out describing it. Okay. So this is, in English, the resistance is equal to the resistivity of the material. So that's based on what it's made out of. Multiplied by the length of the conductor divided by the area. It's the cross-sectional area of the conductor. We have to specify that so you don't get, start to get to the surface area. No, it's so if this is my conductor, so 3-dimensional projection, that the length of this conductor is there. the cross-sectional area is how much area there is across that conductor. So if you picture a wire, most conductors will probably picture easily as like copper wire. They will have a length. The longer they are, the more resistivity they have. Because the further those charges have to flow, more atoms they have to go through. Make it longer, has more resistance to that flow of current. However, if you make it bigger around, what have you done? What you've made in each spot as we move along it, more total free electrons out in that outer valence shell that are easy to move. So if I make it bigger, then there's more ability to have current actually flow through it. So those two work against each other. If you make a bigger conductor, it has less resistance. Rho, by the way, another Greek letter, rho, resistivity. So I'm not going to put numbers up here today. When you read the text, there's a whole table that gives you resistivity of different materials. That's specified by the material. It goes all the way back to how tightly are the atoms that build the molecules, that build the crystal of this whatever material you have. How tightly packed are they? So how many of those external electrons in each atom are available? You can do calculations on them. We're not going to. Or you can measure them in a lab. We're also not going to do that. But when I get to using this equation, you can pull numbers out of the table and just put them into that. And you multiply by the length and the cross-sectional area. Now, for now, I'm sticking more conceptual. So let me give you a couple examples here. And I think mostly common sense once you start thinking about it. If I have a 10-foot cable run, and then I take it, and I need to go longer, and I decide, wow, I would like to do a 100-foot cable run, I have just made 10 times the resistance because it's 10 times longer, assuming it's the same type of cable. Just has further to flow. But that means I will have 10 times as much opposition to the flow of current. So I'll have less current flowing through it. Because it's just harder to flow through that long run. But if I make it a bigger cable, I can offset that by making the cross-sectional area 10 times bigger. Now let me warn you of something here. My area, if I look at this area right here, how would I calculate that area? Well, if you remember back, that's your pi times the radius squared. So I don't need to make it 10 times wider. I need to make the area 10 times bigger. That's a little over 3 times wider because 3.2 something squared is 10. It's not a nice round number, but 3 squared is 9. So I don't have to make it 10 times bigger across. I got to make the area 10 times bigger. So watch out for these. It's very easy to go, wow, something's twice as wide, so I'm going to have twice the area. Nope, if you're twice as big across, you got 4 times the area. Because of the fact that area goes up by the square of the diameter of the radius. Okay, we have a standard measurement we use in North America for wire and its area. It's really based on the diameter of it, but it transcribes to the area. Anybody know what that is?
Gauge.
What was that?
Gauge.
Yeah, gauge. So wire gauges. I'm not going to even give you numbers right now because most of these numbers aren't probably going to mean a lot to you. We'll pull them up in a week or so in calculations. For now, I just want you to get an idea. First of all, wire gauges can be counterintuitive for people because big numbers are smaller and small numbers are bigger. Just like a shotgun for the bird hunters in here, right? 12 gauge is bigger than a 20 gauge. Same with wire. So, standard household electrical wire. 14 gauge is what you'd put on a 15 amp circuit. Standard lighting for a house, standard room circuit for older houses. Now most of them have gone to 20 gauge. 20 gauge, 20 amp. 12 gauge. It's what you use on those 20 amp circuits for your household wiring. So 12 gauge is considerably thicker than 14 gauge. If you ever work with it, you can tell because it's much harder to bend and make it work around corners and pull and stuff. So it's much, much thicker. But if you just looked at the ends of one without it next to the other, you probably wouldn't even be able to tell for sure which is which unless you work with it all the time. Okay, so 12 gauge, 14 gauge household wiring. If you look somewhere, now probably if you're going to have the plug-in for a computer or stereo system or TV or something like that, it's probably going to be even less than these, so make 16 or 18 gauge, somewhere in that range. The wire we're working with in class is mostly 22 and 24 gauge wire. So you can tell it gets pretty thin pretty quickly. If you go up to something like 8 gauge, I mean, you're not going to bend that without grabbing onto it, pliers, and maybe needing 2 people. But you can do it, because that's how you do industrial, high power wiring. I mean, you go all the way down to 0 gauge for high power. By the way, I've run out of numbers. Anybody know if I need something bigger than 0 gauge, what do I do? You go to double watt, triple watt, and quadruple watt gauge. Watt is 0. We will not work with any of that here. Forklift to bring it in, but it goes up that high. If I get down to 26 or 28 gauge wire, that's the little tiny wiring we would do with maybe some potential connections and stuff in here. So it goes up and down pretty quickly. You can look all those up. All of those gauges have a standard diameter that they represent. So like again, that's in your reading this week. There's a whole big table. Looks like it was generated in Excel, about probably Excel 95 or something usually, and it's just sitting there. But it has all those numbers. They would be measured in thousandths of an inch or mils, which is you don't use every day either. But I do stick with all those because we're in North America. If you get outside of here, they'd all be millimeters. But. Okay. So I want you to understand a little bit about gauging, and I want you to understand a little bit about what wiring is. Now let's talk about, there's 2 types of wiring we use here, and I'm just going to talk a little bit about application. If I'm doing household wire, it's solid. That means if I look at that wire, anybody ever done anything with house type wiring, wired up a circuit or something? Yeah, 1 or 2 of you maybe. Yeah, it's kind of, you have wire you buy at the store. You can go to Lowe's or Home Depot and buy it in bulk. And if you look on the end, it's just a solid piece of copper. You actually have 3 of them, or 4 for 3-way lighting, and a piece of Romex cable. Now, if you look inside, like the power cord for, say, an amplifier or something, all the wiring inside, it's probably stranded. In other words, it has, instead of one solid piece of wire, it has a whole bunch of wire that's twisted together. It's a lot easier to maneuver back and forth. If an individual wire breaks, it's still probably okay to carry current. Easier to maneuver. I have some of that in here for us. I would encourage you not to try using it too much just because it's a little harder to work with. It's easier to bend and move, but it's harder on the ends because you have all those wire strands hanging out. I don't really care if you try to use it, but there's some wire over there. Use it for speakers or something like that. Okay, what's my standard wire made out of? Copper. Yeah, copper. Why do I use copper? Well, there's a bunch of reasons, but yeah, go ahead. You can answer.
It's extremely common.
It's fairly common, yes. But it's not the only reason. There's a lot of other things. There, yeah, but
That's like the second best rating for conducting.
so that's the thing. What are all my conductors going to be? What are all my conductors you think of off the top of your head?
Silver.
Well, just what's the name? Metals. Yeah, iron conducts just fine. Silver conducts very well. Silver conducts better than copper. So why don't I do household wiring in silver?
It's expensive, it's frail.
Yeah, it's expensive. It's also, yeah, it's frail. Silver, I can just grab a wire. Boom, oh, it broke. Copper is strong. Steel is stronger. Why don't I use steel wiring? Yeah, if I try to bend a steel piece of 14 gauge around a corner, I'm gonna get on it with everything and a pair of heavy duty pliers. Copper, I can bend all over the place. Copper obviously conducts a bit better, but iron and steel conduct fine, but they're heavy and they're hard to work with. So there's a lot of considerations that go into this beyond, is it absolutely the best conductor? I mean, is it strong? A lot of houses were wired with aluminum back in the 1950s. Why? We had a ton of them left over from, preparation for World War II airplanes. So it's sitting around. We use it. It conducts well. It holds together well. It's strong enough. Unfortunately, it makes really weird connections with copper, so it's kind of a problem now. It also, when it overheats, it decides to flame easier than copper, so it's got some issues. But yeah, we can use aluminum for all kinds of conducting. Pretty much every metal you think of conducts electricity fine. Some better than others, but a lot of metals are hard to work with or rare. Even copper is fairly expensive. You heard people breaking into steel copper out of places to sell back for recycling. It seems like more work than it's worth, but people do it. All right, so I got a question. Still got a lot of audio people in here. Here's a really interesting question for you. If you buy, anybody audiophiles? Buy, stereo stuff and all, I'm familiar with it. So if you go buy audiophile equipment, all your connectors are gold, right? If you go ask the salesperson, they'll usually say, oh, gold conducts better than copper. If you're really serious, you're gonna buy that. If you look at your table, gold doesn't actually conduct as well as copper does. So are they just selling you pure snake oil, or is there a reason for that?
Something to do with corrosion, maybe?
Exactly. So it is an interesting thing. The reason I'm asking you this is it's very easy to tunnel vision in here and go, hey, it's the best conductor. Oh, it's the easiest to work. Well, there's all kinds. Some things corrode, other things don't. Copper corrodes when it's exposed to the elements. Gold doesn't. So in theory, if you make all your connectors out of gold, they won't corrode. Now, I will note there's a bit of an irony to that because you generally only do that for audio hi-fi stuff, put in people's houses with full controls. But if you go run live sound on a stage, you're not going to use gold connectors. So, I don't know how important it is, but, so I always want you to take one step back. When we talk about any of these, and think about real-world applications. Think about, why did they choose this over this? Maybe one's easier to work with, maybe one's too brittle and soft, maybe one's too expensive, maybe corrosion. There are a lot of things that go into this, and most of those, your background is already good enough to kind of see that if you just open up and go, I'm not going to just tunnel on the electrical part. We got to use them for everything. Okay, let me talk about another one on this conductor, because I'm going to use it to talk about. I raised my resistance. I like live sound. It gives me good examples of things to use. Anybody heard of brown out? What is it?
It's when power slightly dies, but not all the way.
Yeah, you have a lower voltage. So I decide, we're in Kansas, okay, so let's do a wheat field. We're gonna go have a big, inexpensive, we're gonna try to do like Woodstock 2025 or something, right? Go to a wheat field. And we run power out there. And I get there and I have power, no problem. And I hook and I run a 1,000-foot cable out there and I measure on the end and I go, I have 100 volts here. All my stuff is designed for 120 volts. Probably just fine at 110 or 130. That's brownout. Why? Oh, I ran this cable 1,000 feet and it's designed to be usually assumed more like 100 feet. And all of a sudden, because it has enough resistance to the current, by the time it gets to the end, the voltage is dropped. So I don't have nearly as much voltage or current to power everything. That'd be a brownout condition. And if I plug in my digital equipment, it may not work at all, because it really is particular. And my other stuff will probably sound different. It won't be fully powered. All right. So what's the first step that I do when I do that? Anybody's ever done live sound chart?
Measure for inconsistency.
No, I go get a big cable. Yeah. You can measure it.
That's the solution.
Yeah, no. You're right. But what I was looking for there is the first answer to that. Everybody will tell you if you're, oh yeah, get rid of the, you ran 14 gauge, extension cables, go get 12s or 10s. And you're right across there. And all of a sudden you've got 105 or 110 volts. Less resistance because it's bigger, thicker cable. Also has the advantage that when somebody backs a trailer over the top of it, it doesn't break as readily. But that's kind of a side advantage. What's the disadvantage to using? Why don't I just go, well, let's just use that thicker, heavier cable for everything all the time? Cost a lot more to get that cable. It's a lot heavier. I may need, a couple extra crew to haul that big cable around and move it around instead of a short cable. All right, so these are just practical thoughts on this. Now, when we're working in the lab in here, we have little short wires, and they're, like I said, they're more like 24 gauge. Doesn't matter. Very low voltage, very tiny little currents. That opposition for a cable that long is almost nothing. It's not nothing. That's almost. Okay. So we talked a little bit about wire gauge, materials, resistivity, resistance. When I looked at this week's homework, those are the topics we didn't cover on Tuesday that we needed to cover today. And so I wanted to make sure we hit everything. At this point, I know it's kind of early in the class, but I think if you have questions on anything we're doing this week, I would ask them. Otherwise, I'm going to turn you loose to spend the time working through the lab and making sure you get through that, or if you have homework questions. A lot of it, you come in here a little later. I will remind you. It's about to abbreviate that. You got to watch for your abbreviated assignment, huh? Assignment 1, lab 1. Yeah, I was about to stop. No, I can't. Maybe I should write that all out. Assignment 2. Lab 2. Those are all due today. Okay? I'm not being hardcore. If you need more time on lab 2, get it done. I want you to understand the material first. But we'll be moving on to the week 3 material, assuming you have everything from this week done, down and done by next Tuesday. So, yeah.
So homework is due on Thursdays?
Did I say Thursday or Friday?
Thursday.
What?
I thought it said Friday on Black.
Okay, Friday then. We'll do it Friday, but I'm not here on Friday, so you got to turn it in remotely.
So everything's due on Friday?
Yeah. Thank you, Fridays. Listen to Blackboard, it's more right than I am up here. But thank you for asking. So yeah, and I'm not going to give you, if you turn it in Saturday or Sunday, I'm not going to knock points off, but I will, if I grade them all, it may take me a week or so to get back to it. My goal of those due dates is mostly to make sure you know, hey, I need to get this stuff done, so next week I'm ready to move into the new material. I don't want to be going back and explaining the older stuff when we get into it. Okay, this week in lab, measuring current. Last week was measuring voltage. This week's measuring current. So remember, break the circuit, measure right at the spot where you broke. Do not do anything where you try to connect my battery from positive directly to negative through my ammeter. If you burn my fuses up, I have the right to ground at you about it. Okay, with that, other questions? I have 12 of you in here. I have 14 enrolled, so I'm curious who. For those of you who are not here, let me know, I guess.